can go to the evolution story, which teaches that over long periods of time, the continents sank and they came back up. And they sank and came back up. But the question I have for anybody believing that is, did anybody ever observe that? And the answer is no. But did you know there's over 200 legends from cultures all over this planet of a flood, but not one of the evolution model? Also, all over this planet, we find fossil graveyards. Graveyards where we find thousands of creatures all buried and fossilized together. Now, hold on. First of all, how do you become a fossil? Well, one thing we know for sure is you don't fall over dead and become a fossil. You must be buried rapidly by the sediments to keep the oxygen out and the scavengers away. So then how do you get thousands of creatures all buried and fossilized together? Well, one thing we know for sure about that is not by long, slow processes, which rules out most of the evolution model. It takes a catastrophic event to do that. And we find these all over this planet, which is consistent with a worldwide flood. Now, some more geology. May 18th, 1980. Something very significant happened in the state of Washington called Mount St. Helens, a volcano. May 18th, 1980, at 8:32 in the morning, an earthquake of magnitude 5.1 struck that mountain, Mount St. Helens. At that point in time, the largest observed landslide in history took place. The entire side of that mountain slid down into Spirit Lake, causing a water wave to go about 800 feet high on the other side of the mountain, washing down thousands of trees back down into the lake. Following all that came the pyroclastic flows, hot gas and ash coming down that mountain about 70 miles an hour at over 800 degrees. Following that came the mud flows from all the snow and the ice at the top melting, all the vapor coming out of the mountain. Mud flows coming down that mountain about 50 miles an hour with such force, some of these mud flows went almost 20 miles beyond the mountain. And what was the result of all of this? Well, before I talk about the results, I want to talk about how large canyons are formed. And to find that out, we can open up our textbooks. And the typical explanation in our textbooks goes something like this. We have to have rivers running through there for hundreds of thousands or millions of years. And we might have to have some geologic movement such as earthquakes going through there. But you know there's only one problem with that explanation. It's mostly just a story we find in textbooks. Because this canyon we're looking at here is nicknamed the Little Grand Canyon by Mount St. Helens. It's 1/40th the scale model of the Grand Canyon. It has some of the same geologic formations we find in the Grand Canyon. Now this canyon is very deep and extends for long distances. And the question I have is, how long did it take to make this canyon? And the answer is 1 day. Oh, come on, Mike. How do you know this only took 1 day? Well, that's easy. See, one day it was not there, and the next day it was. You know what that means? We have observable evidence that large canyons can and do form rapidly. We have the observable evidence to support that. Now, here's another area in the state of Washington. In eastern Washington, there's an area called the Scablands. It's a large, barren area, not much there. Just solid rock. In some places, this rock is almost 1,000 feet deep. And carved all through this solid rock are many channels and canyons like you see here. Some of these canyons over 500 feet deep and extending for miles. And the question we have is, how long did it take to make these canyons? And the answer is, just weeks. The Missoula flood came through there and carved these canyons out through solid rock rapidly. You can go to any university bookstore today, pick out their geology textbook, and every single one of them today will say these canyons were formed by a catastrophic event. The power of water to create large geologic structures rapidly is well known. Then we can turn to other geologic processes. We look at the sides of canyon walls. And we see all of them down these canyon walls. They're made up of many thin layers. Sometimes these layers are only millimeters thick. And the normal interpretation we see is each one of these layers took a season or year or years to lay down. So if you were to look at this canyon here and count up all those layers, you would assume this canyon must be tens of thousands of years old, and your answer would be absolutely Wrong. See, this canyon by Mount St. Helens was formed in one day in 1982. As those pyroclastic flows came down off that mountain along with the mud flows, they sorted out the sediments into thin layers rapidly. The requirement for long ages is not there. But that's not the only way we get thin layers of sedimentation. During earthquakes, there's a process called liquefaction. That's when we have an earthquake in an area where we have underground water, underground springs. Sometimes that water will swell up to the surface, turning the ground into quicksand, and buildings will literally sink into the ground. And when that water settles back down, it sorts out the sediments into thin layers rapidly. Where is this requirement for long ages coming from? Not from the Bible, not even from science. It's only coming from a model called evolution. But those aren't the only ways we get thin layers of sedimentation laid down. The geologists today agree that over 50% of the Earth's sedimentation, over 50% was laid down by underwater landslides called turbidites. Now, wait a minute. What would cause so many underwater landslides? Well, just a thought here. How about a worldwide flood? It seems to match the data. It's been observed that these underwater landslides, these turbidites, have laid down tens of thousands of square miles. Not feet, not yards, but tens of thousands of square miles of thin layers of sediment in a matter of hours. Where is this need for long ages coming from now? Not from science, not from the Bible. It's only coming from a model called evolution. And then we can turn to a strange fossil called a polystrate fossil. Now, what is a polystrate fossil? Well, before I talk about a polystrate fossil, I want to talk about coal. How is coal formed? Well, again, we can turn to our textbooks. Now, one of the things you notice I like to do in a lot of my talks is I tend to pick on textbooks. Now, why do I do that? The answer is easy. They deserve it. Now, how is coal formed? Well, our typical explanation is, first of all, we've got to start with swamp vegetation. Then we're going to have long periods of time for that swamp vegetation to gradually decay and mix with other minerals and elements. Then we're going to have more long periods of time for it to slowly decay and turn into peat. Then we're going to have more long periods of time for that peat to slowly harden and turn into coal. And there's only one problem with that explanation. It's just a story we find in textbooks. Because you see, all over this planet, we find polystrate fossils. Those are tree fossils. Poly meaning many, strata, straight strata, many strata. Tree fossils spanning many seams of strata, specifically in coal beds, many seams of coal. Now here's the situation. If that coal took hundreds of thousands or millions of years to form, none of those trees would be there. They'd have all rotted in just years. But yet there they are, observable evidence that that coal had to form rapidly. You know what else we discovered about these polystrate fossils? These fossils spanning many seams of coal? They did not grow there. We look at the root structures, they're not there. The sediments around them show they did not grow in the coal. Well, if they didn't grow in the coal, then how did they get there? Well, to understand that, we can go back to Mount St. Helens. Remember that water wave that washed many thousands of trees down into the lake? When the eruption was all over, we had a log mat sitting in Spirit Lake of over 1 million logs, all just floating in Spirit Lake. Then we noticed some of them got waterlogged at the root end.